Good morning. I'd like to thank the HPC Advisory Council for letting me come and talk to all of you this morning. I'd also like to thank all of you for getting up at this computer science ungodly hour and choosing to come hang out with all of us and talk about some pretty cool topics. I would be remiss if I didn't mention that I'm presenting the work of a lot of people, more than I could possibly list, at the laboratory and with our partners. So don't for a moment think that everything you see on this screen is a result of just my work. So I'll talk a bit today about the Sierra Supercomputer, since that's what I was asked to come talk about. But I also want to talk about collaboration. And I think that this space is an example of exactly the kind of collaboration that we have to have if we're going to continue to make progress in HPC. I'll talk about Coral, which is a collaboration of Oak Ridge, Argonne, and Livermore, which are national laboratories that have collaborated on supercomputer procurements, right, gathering requirements and trying to decide what architectures are going to work best for us, and also making it exciting and lucrative for vendors to bid on these procurements, because there are multiple winners and everybody has an opportunity to play. We recognize that it's a huge investment to even prepare a response to a large supercomputer procurement. And then I also want to talk about the IBM, NVIDIA, Mellanox collaboration that was a response to Sierra and Open Power, which is kind of the framework that allows them to collaborate that way. And then we'll also talk a bit about the Livermore Lab mission and how we use high-performance computing to get our work done. So Sierra, these things start quite a long time before they come to fruition. The machine is out there on the floor now, or at least part of it, right? It takes a year to build one of these things, even after you start getting stuff on the floor. But where did it start for me? Well, it actually started for me when I was riding my bike like 5 years ago. I don't remember the exact date, but I absolutely remember the bike ride. We were just starting to think about Sequoia, which is our current HPC platform, our current advanced technology system at Livermore. And I was the sysadmin working on that system. And I was out on a bike ride with our computing center director, Kim Cups, and we were talking about well, what's the next thing, and what would I do next? I've done a few of these things. And she said, well, there's this pre-Exascale procurement that we're just starting to think about. What's a pre-Exascale? Like, this is the computer before you buy the computer? Like, what is this? But that was where the idea of Sierra and the fact that I would have some significant involvement in it, where that started for me. So the Sierra system is one of the advanced technology systems that's part of the ASC program at Livermore and the Tri-Labs. And you can see we have this series of systems, both the advanced technology systems, so those are systems that are usually larger, at least partially, if not fully, vendor integrated. They usually have one or more technologies that aren't really available in the commodity market yet, and they push the scale of those technologies. We also have these commodity technology systems, and this is very bread and butter. Everybody in the room and our users, for that matter, they know and they love these kinds of systems where they just want, I want as many nodes of this as I possibly can because I'm going to do my day-to-day work on this, pizza box with an interconnect HPC system. So we do both of those things, and you can see how they overlap. So Sierra is the ATS-2 at Livermore, and it's coming online right now. And you can see that we alternate back and forth between computers we cite in California at Lawrence Livermore and computers that we cite in New Mexico as a partnership between Los Alamos and Sandia National Laboratories. And later on in the talk, I'll talk a little bit more about the mission space and what those laboratories are using these large computers for. So a little bit about the architecture. So the Power 9 processor is the heart of this thing. But all of the flops come from the GPUs. And I think everybody here has seen this writing on the wall for a little while. But this is the first really large accelerator-based system for Livermore. So we have 4 NVIDIA Volta GPUs in each node. They're connected by NVLink 2.0, which gets us two really important things, right? It gets us high bandwidth to the GPU, more than we can get over the PCI bus. And it gets us actual memory coherency between the CPU and the GPU. And that's the really exciting new thing. It means that while it may not be the most efficient way to get data to and from the GPU, it does mean that codes can start to port right away to the GPU without having to completely change the data model in their code to get started. So for us, that was a game changer. That's the kind of thing that actually enabled us to go to a huge GPU machine and reduce the risk enough that we felt, yes, we can totally make our large suite of very large applications run on this thing before it's obsolete, right? That's really the challenge. So in the node, there's some stats. Memory, it's probably important to point out that there's also 16 gigabytes of high bandwidth memory on each GPU. All of the advanced technology architectures that we evaluated for Sierra had this kind of a model, where there's some kind of really fast memory, and there's not very much of it, and it's close to the biggest processor. And then there's some additional level of reasonably quick, normal DDR memory, right? And then there may be some level of like flash storage or a burst buffer and file system, right? Lots of levels. But this fast memory really close to the CPU was a feature in all of the systems, whether they had accelerators or whether they were homogeneous systems. So then we take all this stuff, put it in a standard 19-inch rack. We're using Mellanox EDR, 2-to-1 tapered fat tree. So that means that every node has two connections into two leaf switches in the rack, and then each of those leaf switches has a connection to one of 9 director switches. And I have some slides on that later. But that's a low-risk part of this procurement, right? EDR's been around. Probably half the people in the room or more have EDR on their systems today. And then there's the whole system. We will have a 154 petabyte file system, 1.5 terabytes a second bandwidth, which is a lot of bandwidth, but it's still a much lower bandwidth ratio than what we're used to on these kind of systems. And I'll talk a little bit about the burst buffer later on that kind of gets us around that. And maybe the last thing to point out that's exciting on this slide is that this whole thing is only 12 megawatts. That's a ton of electricity, but the flops per watt is actually really coming down as a result of accelerators. Now, from an application perspective, these giant HPC systems always have the same effect for our users, which is, it ruins their whole day, right? Because you say, okay, you've got an application, it's got 1 million lines of code, you've been developing it for 15 years, and we've been delivering you a certain kind of computer for all of those years, and now we're going to get you something completely different. That's not hard, right? And that's what we did, right? The Blue Gene systems, those are big, giant, homogeneous, 16 cores, which at the time was a lot of cores, right? So we could potentially call that many core. And we scaled, to millions of MPI tasks with MPI anywhere, which at the time people thought you couldn't do. So that was the scary thing for that system. Well, now we've done it. And then we're going to do something different, right? The cores aren't lean anymore. The nodes are giant. And we're going to go to a heterogeneous system, right? We're going to say you have accelerators and you have CPUs and you have to move data back and forth. But hey, at least we have this NVLink thing that will magically make it okay. Not really. And so it's really a big 180-degree turn away from what we were doing to something different. And it's not the first time we've done this to our application teams, but it's where the technology is. And so we have to follow. So at Livermore, we are firmly in this camp for a while. We have decided that accelerators is where the industry is going. This is how we're going to find at least one viable path to exascale systems and likely beyond. So we're going to make a really big investment in this kind of technology. Now, none of this stuff is without trade-offs. And during this procurement, one of the things that hit us, and it's probably hitting everybody in the room, is that DRAM costs are way higher than anybody thought they would be if you tried to forecast 2 or 3 or 4 years ago to what they might be today because you were going to buy a computer, they're just a lot higher. And the vendor doesn't want to take all the risk in that. And so we have a shared risk model with our vendors for DRAM prices in particular. And we evaluated a couple options to close the cost gap. We said, well, we could just buy half as much memory. That's easy, right? It costs twice as much, buy half as much, done. You don't need a room full of PhDs to figure that one out. But you have to figure out whether you can do that and still get your mission done, and maybe that takes a room full of PhDs. The other thing we evaluated was tapering the network. So we used to have a full bandwidth, non-blocking fat tree network on this system. And we said, well, if we buy half as many of these really expensive director level switches, what does that look like for our application space and our use cases? And it turned out that it didn't look that bad. So what we did was we selected both options. And then we took the extra money and we bought more nodes. So the projection is we'll lose less than 1% performance by tapering the network, and that our applications will still fit in the available memory. And so we can actually get about 5% more nodes, and that's pretty exciting. This is kind of the obligatory eye chart slide, all the stats of the systems. The most important thing to take away is that when we buy one of these big computers that's destined for our classified network, never to see the light of day again and do really important work for the nation, but doesn't show up for people, most of the people in this room, for example, we buy other systems. So we have an unclassified version of Sierra that is, an order of magnitude smaller, but still a powerful system in its own right. And that will be deployed right after Sierra. Nodes will stop being delivered for Sierra here in a couple of months, and we'll immediately start delivering compute nodes for USierra. So that's great. And then we also have a system called RZ Sierra, which is another order of magnitude smaller, sits on one of our restricted networks, but still unclassified. And not on this slide, of course, is a tested development system that we use so that we can make sure that the new software and new ideas work before we disrupt everybody. But the key thing is that it's the exact same technology in all these systems. It's not like the unclassified system gets less GPUs or less memory or less anything. It's smaller, but it has all the same compute elements. Now, my colleague Robin Goldstone was out here 2 years ago, and she put up a slide that looked very much like this one with all the targets that Sierra's going to do all this stuff, right? It's made of unobtainium. It's in imagination land right now. But we're going to do all this stuff. And that's always a little bit nerve-wracking because who knows if we're going to do all this stuff, right? Both the laboratories and their vendors are making all sorts of projections into the future about what technology might look like and how much it's going to cost, and therefore how much we're going to be able to afford. And what I did is I took her projections, which were the procurement projections, and I color-coded them. So all the green ones, these are things that we have either already measured that we did with the procurement, or ones that we're absolutely on target to meet, but we just don't have enough computers in place yet to actually measure and check the box. And the only one that we didn't meet is the aggregate memory of 4 petabytes for the system. And part of that is when we generated the procurement, we were envisioning a huge node count across the system. So to have any amount of memory that would be reasonable on a single node, it ended up with this huge memory space. And there were also some specific application needs that said we need to fit a problem this big in memory. We didn't meet that because memory costs were high, and we got this architecture that has really powerful individual nodes. So unless you start putting truly massive amounts of memory per node, you can't get to 4 petabytes of memory. But we did get the greater than equal to 1 gigabyte task. In fact, more than the 2 gigabyte preferred, so that all worked well. Beat the power target by a lot. The failure target is interesting because it requires a lot of restarts and a burst buffer to make those restarts fast, and some libraries to automatically handle that. So there's a lot of technology behind meeting that goal. The architectural diversity, right? We selected Sierra. Argonne National Lab selected a different architecture, so we were able to select 2 different viable architectures. So that was very exciting for the Office of Science, which has 2 computing centers operating at any given time, and they want to have different kinds of technology, but they were on a single procurement. So just a lot of excitement. And then peak performance is very above target to what we wanted to get to, although the applications will have a lot of work to realize that. So let's talk about the collaborations. Sierra is part of Coral. It's the collaboration of Oak Ridge, Argonne, and Livermore. And this is the important stuff going forward, is finding some people to collaborate with to meet both your and their mission needs, right, to make everything stronger. So we had collaborated with Argonne already on our Sequoia and Mira procurements, and that worked out pretty well. And so we also hooked up with Oak Ridge National Laboratory, which is a huge Office of Science, open science laboratory in Tennessee. And we said, we're going to throw out one procurement because we're going to get computers in about the same time frame. So that makes us a good set of labs to partner up. And what we're going to do is we're going to award a bunch of contracts as a result of this. We're going to award to at least 2 different vendors, at least 3 different procurement contracts. And in this case, it ended up 2 different NRE contracts, so that's non-recurring engineering. So that's basically direct technology investment. That's money that we're going to pay to them to develop new technology that will be useful in the system. It's not just pure research. It's very applied research. But even if you get to a go, no-go decision with the computer, you still get paid for your research. So it helps remove risk for the vendors so that they can actually attack some of the problems. So this was super important to making this happen. It would not have happened if we couldn't collaborate to both get all of the intellectual property that the other laboratories who are doing this kind of work have at their disposal, and to make it exciting for the vendors to come up in here and actually bid on this stuff. The other collaboration that we didn't know we were going to get at the beginning, but has happened, is open power. And this is the framework that allowed IBM, NVIDIA, and Mellanox to all get together and bring their strongest technology elements together with really, deep cooperation to provide this system. So that means that instead of just having a CPU and a PCI bus and a GPU that work the same way they always have, they said, no, we're going to do NVLink, and we're going to make, a whole new way of transferring data between the CPU and the GPU. We're going to share a lot of intellectual property, and we're going to make this work. That couldn't have happened without vendor collaboration at an unprecedented level. Similarly, Mellanox has switch-based collective technology that has to tie into the MPI that's provided by IBM. So again, that's a super tight collaboration to actually get all this stuff to work. So the NRE contract I talked about a little bit. This is where we were for the last several years, and this is the work that was just starting up a couple of years ago when we talked to this group before. And they spun up 8 groups to collaborate between both the vendors and the laboratories, everybody working together under a common goal, sharing very freely with all the intellectual property agreements in place that allow us just to work. And that was fantastic. And most of these groups in their NRE contract, basically, they're done. But all the groups stayed together. They said, okay, NRE contract over, but all of these relationships that we've developed, these are the same relationships that are going to allow us to make the production system actually work. So these groups are still meeting. They're still, pushing the state of the art, and they're making, things work for the user community that just wouldn't have happened without that level of collaboration. I'm just going to give one example of an NRE collaboration that had huge impact that nobody expected before spinning up the collaboration. So the original plan of record had a pretty good file system, and that was exciting. But some folks at Oak Ridge went out and did some research and said, we think we can do better. We think we have an idea that we can do something that's a little more cost-effective, a little more dense from a storage perspective, a little bit faster, and we think it would cost about the same. What do you think, IBM? And they went out and noodled on that for a while, and they said, we think you're right. And so now we have a 154 petabyte system for our procurement. And that's basically a denser solution and a higher capacity drive solution. Performance is better, so we still have sufficient spindles to meet our performance needs. And we also did a lot of work on the Spectrum Scale software. In particular, one of the things that made Spectrum Scale a little bit challenging to work with before is a number of the metadata areas. In particular, accessing a lot of files in a single shared directory. And they've done a ton of work to improve that through this working group. And we're going to see the results of that work in production code in like the next month, and be able to put that out there on the system and take it for a spin. So partnering at this level really allows us to improve the ecosystem and get things done. On the vendor side, IBM partnered with NVIDIA to project for our benchmark applications whether they would port well to the GPU. And without really close collaboration on the vendor side, they couldn't have done this, right? They had to say, we're going to take this chip, Power 9, that doesn't exist yet, and this GPU, NVIDIA Volta, GV100, it doesn't exist yet. We're going to connect it via this magical bus NVLink that doesn't exist yet. And we're going to say the performance is going to be this. Like, if you think that's easy, you're crazy. But if you think it's possible to do it with enough confidence to sign up for it in a contract, you might not be crazy. And that's what they did. So it's very exciting that they were able to collaborate at that level that early in the process. And that makes our job easy in selecting a system. If people can, come together, share their intellectual property, and make these kinds of, very realistic, fact-based, evidence-based projections about performance. So, applications. 3 to 4 years before there's going to be any kind of a computer to even try things on, we said, we're going to select this solution. And the application people were like, oh man, this is not what I signed up for. And we said, no, there were a couple application people on the procurement team. They signed you up. And now the system's delivery is underway. They've been running on the early access systems for a while. So how do you get from there to here? Because you don't want to have the system arrive and then start porting. And that's what's happened in some of our past systems. System gets here, you start porting. It takes a year or two to get your code really running well. Now you've wasted a third of the useful life of the computer. That's no good, right? So we wanted to be ready to run, ready to take off at the moment the computer arrives. And this is something that we really pushed much, much harder on than we had with any of our previous systems. And this concept came to us from Oak Ridge, right? Part of that collaboration, and that is the center of excellence. So you take vendor experts from IBM, NVIDIA, and Mellanox, you park them at the lab, you get them security clearances, you get them working on the applications of interest, you run classes and hackathons, you select a set of applications that are representative across your application suite that you're going to try to make this kind of progress on. And then you see it's working so well that you select a whole other set of applications from our institutional program. And everybody comes together to really push codes in that direction. Then when the early access machines show up, you can start to try this stuff. And you can really get to a place that wasn't available to us before, right? If we waited to port to GPUs until the final machine arrived, we would not have been able to have success. And throughout this whole thing, something that was just really driving for us is the idea of performance portability. Okay, we're going from homogeneous to heterogeneous, right? And this is a really painful transition. Well, next we're going to go from heterogeneous to I don't know what. Is there anything we can do to make the next transition easier than this one? So that's the idea of performance portability. One example of a performance portability abstraction that's been developed at Livermore is Raja. So this is a standard C++, relatively modern C++, so compiler support for this kind of stuff is still maturing. But Raja takes a standard C-style for loop like this one, and it abstracts out a few things. So the body of the loop remains basically the same, and in a much more complicated loop, it would still remain mostly the same. But we extract out the actual loop information, right? And we make that a C++ template. And then we say, all right, you can have multiple execution policies. So is this going to run on CPU on OpenMP? Is this going to run on GPU with a CUDA backend? Is it going to run on GPU with an OpenACC backend? You know, how is this going to execute? Or is it going to execute on some other platform? But you keep all of the body of the loop in a Lambda function, so you can just take it with you, and you don't have to change that. So it's really taking the idea of marking up your code to just a slightly higher level, and you pay a penalty, right? You pay a slight performance penalty, but it's not very high in almost all of our cases. And we're continuing to work on the cases where there is too much of a performance penalty. But we're willing to pay a little bit of a penalty, a couple of %, if it means that the next time we make an architectural change, we can just flip a switch, change out the execution policy to the new thing, or change out the indexing policy for the data movement to a new thing. So that's the idea with Raja, and we're using this in our codes. So, and that's, by the way, is on GitHub, GitHub/LLNL/Raja. All right, let's talk a little bit about those early access systems. So Sierra is showing up now, but a year ago, this is what showed up. So Power 8 Plus, so that's Power 8 with an NVLink 1.0, not coherent shared memory, but it does have increased bandwidth, and there's a software unified virtual memory layer that allows people to write code as if there was coherent memory and just pay a performance penalty. Similar amount of memory. Lets us try all the compiler options that are out there. And this is when we really find out, is the rubber meeting the road, right? Does all of our work that's been happening kind of in seclusion and on a couple of x86 GPU systems, does it get to a place where we can really, really use it, and does it do real stuff? It's got the same file system, right? So that's the first step of getting real codes on a new advanced architecture. And we bought 3 of these things, one in our classified network, one in our unclassified network, and one in our restricted network. Should not surprise you, those are the same networks that we're putting Sierra systems in, so everybody gets a chance to try it. We did put solid-state disks, NVMe, in one of the systems, which is one of the key technologies in Sierra for the burst buffer, so we could try all of that stuff. So these centers of excellence started out 5 years ago. They started out doing a lot of training and classes and deep dives, and maybe some key benchmarking kernel exploration, right? Kind of very basic stuff, figuring out, what can we do to move to this new architecture? What does it look like? What kind of abstraction layers should we make in order to enable performance portability in this architecture? And then they start exploring with proxy apps. So those are applications where you don't take a 1,000,000-line code app and try to port it and see if it's fast or not, right? You take a proxy application that has some key kernels in common, and then you port that and you explore with that. It's much, much easier, right? Now, the early access systems start to show up, and you can see we start to spend more time in this section, right, on early access systems and actually running code and running real applications and taking everything that we've been learning over the last couple of years and putting it into production codes. And then right now today, we are at the delivery of Sierra. We have users starting to run on our test system, and they'll be running on the big Sierra system this week, right? So that's just really exciting. And then we're going to deliver some early science results where people run on large portions of the system for a significant amount of time and get to try some really exciting open science. Now, we started this thing as part of the contract and said, all right, we're going to take our ASC codes, we're going to port them over to this platform, And we're going to use this strategy to get our key programmatic applications. And then we said, well, we don't want to leave the whole institution behind, right? All the unclassified codes, all the open science codes, right? Things that are used for earthquake simulation and climate and jet engines and you name it. So the institution then funded the ICOE, the Institutional Center of Excellence. So we've got this whole group that really has all of the codes, all of the vendors, everyone in the computer center working together to get the applications to succeed. Instead of just saying, all right, here's a computer, it's got a bunch of flops, whatever those are, good luck. Now we really have an opportunity to enable people to succeed. So the Sierra COE is what we started with the subcontract with IBM, plus the institutional COE, plus all of the staff, the advanced architecture specialists, right? Everybody working together to enable science. So some of our applications have been, moving towards GPU. And we started going, well, we hope some applications may be able to make use of this, but we'd like more and more to be able to do it. And we've gotten to a place now where a lot of our applications are really porting quite well to the GPU. They're far along. They're seeing very real speed ups. There are still a couple challenge areas. And these particular speed ups are all observed as two power rate CPUs versus running with the GPUs enabled. So I don't, this isn't an old computer to a new computer, but this is new computer with and without GPUs. Are we actually effectively using the new technology? So we're doing pretty well at this point, and we don't have any particular reason to suspect that this isn't going to go, really quite well. And as a person who's been involved in this procurement, it's really gratifying, and it makes me really jazzed to get up and go to work every day to say, well, we've been doing this thing for years, and it was a challenge, and it's actually going to work. That's just really exciting to me. Talk a little bit, just a few slides, about the mission of the laboratory. So we bought all this giant computer. What are we going to do with it, right? What do you actually do with this kind of a system? So these are all the mission areas for the lab, right? So you have intelligence and data science kind of stuff. You've got biosecurity, where you're evaluating all sorts of computational biology problems. Counterterrorism, this allows us to look at simulations of potential threat options and potential targets, evaluate countermeasures, whether they're going to work or not. Right? It's much better to evaluate in the computer whether something is going to work before you build it and find out that it doesn't. Non-proliferation has always been a huge area for the laboratory. It's important for us to be able to know what the signature looks like of materials in transit and that kind of thing, so that they can be interdicted. Defense, so it's not just nuclear stuff at the lab. There's a lot of non-nuclear conventional work where you use computer simulation to greatly accelerate the design time frame for new systems. Basic science to fuel all of this stuff, energy research, into fusion and that sort of thing, and where this all started for us, which is in the nuclear weapons stockpile. And I'll talk a little bit more about that as an example. So here we are. This is the National Museum of Nuclear History in Albuquerque, and you've got Little Boy and Fat Man in the foreground, and then you've got this car in the background, which is a beautiful period piece. So what are we doing with the computer, though? And I'm going to talk a little bit about that in broad terms. So the United States hasn't tested a nuclear weapon since 1992, right? We don't blow these things up yet, anymore, rather. But we have to guarantee, right? Our laboratory director and the director of Los Alamos and the director of Sandia have to write a letter to the president every year that says, I certify that the nuclear deterrent is safe, secure, and reliable. That means it's going to work. It's going to work when you want it to work. It's not going to work when you don't want it to work, right? All of these things, but you can't test it. These are really, really complicated devices. They have all sorts of crazy materials in them that have properties that aren't the same as the materials that we work with on a daily basis, right? So how can you possibly do that? I mean, what does it even mean to do that? And the car comes in there. So imagine you've got a car in your garage and it's 40 years old. It's a beautiful car. It's impeccably maintained, spared no expense. You haven't started it in 40 years either. In fact, you can't start it in 40. You can't start it, not ever. You can change out the fuel, you can change the oil if you want. You can even take that rusted part and replace it with a part that's similar. They may or may not make the exact part anymore, but you fabricate it in the shop and it looks pretty similar. So life is pretty good. It's a nice car. Are you certain that you can jump in the car, turn it over? It'll turn over on the first go, and you can go drive 100 miles an hour and then stop in the same distance that you did when the car was new. That's what we're trying to do with the computer for the Stockpile. So you're allowed to test things. You're allowed to take the tires off the car or make a facsimile of the tire and make sure that, you can take an X-ray it and make sure that there's no hairline cracks in the hub or whatever and all that kind of stuff. But you can't actually start the car. And of course, you got a garage full of these cars, so you can even take one of them completely apart and look at it, but you can't start the car. So that's what we're trying to do with the computer. And we use the ASC program to do that, right? Advanced Simulation and Computing. And so we're using, really pretty advanced simulation technologies on both our weapons codes, weapons science. That's like the material science around these aging systems, the computing platforms, and all the supporting infrastructure, and of course, a small army of people to get this job done. So this is a computational surrogate for nuclear testing. And I don't usually try to just read my slides to people, but it's central to U.S. national security. Our national security depends on the idea that we believe our nuclear deterrent is reliable, but more so that any potential adversary believes the nuclear deterrent is reliable, right? Nobody is going to have pause about doing something terrible if they don't think that the deterrent is real, right? If they don't think that this is a thing that could happen. And so that's just so important, right? Not only that it works, but that everybody else believes that it works, that the science is real and verifiable. So we also play an important role in non-proliferation, emergency response, and nuclear forensics, right? All these things, there's this whole class of experiments, both in nuclear weapons, but other places as well, where you don't want to run the actual experiment in the real world because it's really expensive, or it's really messy, or you don't have anywhere to do it, or it takes too long, and that's where our simulation capability comes in. So why do we need such a big computer? And the answer to that isn't probably terribly hard for the people in this room to understand. But the further we get away from our tested base, right, 1992 and before, the more materials change, and the more of those little repairs you have to make on the car, right? The more that stuff happens, the more you need to validate not against some test that tested something that's not exactly the same as what we have today, but you have to validate against the basic science that drives it. So we're talking about ab initio simulations. We're talking about atomistic simulations where we use atomistic simulations where the rules are simpler, right? Force equals mass times acceleration, right? Like high school physics level stuff that we really understand really well, to validate more complex continuum models, and then in turn to validate full-size objects, right? So we're trying to get from submicron and micron scale to validate models that we can use for things that are this big or the size of the stage or something, end to end. So as we go from 2D to 3D, or as our simulation space volume gets bigger or the complexity gets higher, maybe we have higher order models and that kind of thing. All of that drives the computational requirements up. And so you can see we're already in a regime where we need exaflops. And that's still a few years off. And there's no particular reason to think that anybody would want to stop improving the fidelity of the simulations. Another thing that I don't really have a slide in here for, but uncertainty quantification, it's in here a little bit. So the idea there is you're doing some multidimensional parameter study to try to kind of find the bounding box of how things relate back to that tested base. And so you're running many, many, many smaller simulations instead of one gigantic one, which is actually the problem space that Sierra is meant to solve. And that's why reducing the network bandwidth didn't hurt us so much, because the simulation space can actually stay within that full bandwidth rack unit some of the time and not have to expand across the whole system. So what can we do with some of these new software technologies that people are talking about, right? This is HPC Advisory Council and AI, right? So what happens with AI and machine learning technologies? Can we steer our workflow and say, hey, there's something really exciting, something's really exciting happening right here in this area of the simulation. Maybe we need to spin off a full resolution simulation or a 3D simulation of that one area and resolve what's going on there. We have some experimental technologies in machine learning and neuromorphic computers. So these are really exciting computers that instead of processing the way we're used to, they work kind of like your brain, where you take inputs and you kind of build up a charge if you have inputs that meet the condition, and then if you have enough, you fire, and then that output can become an input for another set, right? And that's not how our algorithms are written, but it's really efficient to build a computer like that. It's really fast, and it's how your brain works. And we have some evidence to suggest that our brains are pretty capable. Your brains, anyway, but we have some evidence. So lots of technology that's just really exciting to investigate. With Sierra, we're hoping to take some machine learning technology and apply it to our workflow. So if you're doing one of these uncertainty quantification runs, you can actually ask the computer, where is the uncertainty? Please generate some simulations that will help you answer the question, right? So decide what parameters we actually need to study. And then we'll run some high-fidelity simulations of all of those things. And then we will crunch those all together, kind of look what the new parameter space looks like, find out where the uncertainty remains, and feed back into starting all over again. So Sierra and EA systems that came before it are beginning this accelerator-based computing era for Lawrence Livermore. And there were some significant advantages that allowed us to select this and take a risk on the accelerator-based methodology. So it's very power efficient, right? We're able to go from 20 petaflops on Sequoia to 125 petaflops on Sierra, and the power budget increased, 10 or 20%, not an order of magnitude. That's huge, right? There's the cost of computing is beginning to be dominated by electricity, and in the next generation of computers, it may very well be. It may be that buying the computer is kind of a drop in the bucket eventually compared to the cost of the electricity for the computer. And of course, the humans who have to run the computer and work on the computer and develop software for the computer. We thought that this represents a clear path forward for performance portability. There are ways to write for this architecture that will generalize to other homogeneous vector architectures and that kind of thing. You can write your code in the same way, expose the parallelism in your application using the same set of abstractions, and get performance on other computers. The fat nodes, right? You have less endpoints, it's a simpler network, that's great. There are some downsides. You have to have more bandwidth per node to accomplish the same communications. So that's a balance. The other point I want to make wrapping up is that broad collaboration between as many people as you can possibly get is just key for not only developing but also utilizing these HPC systems. I think it was this past year at SC, Gordon Bell gave a talk, and he said, you know, look, there's this, he plotted the number of collaborators per Gordon Bell winning submission over time. And he says, look, the average number of collaborators is trending up, you know, on a linear progression. It just takes more people time and more collaboration, more creativity from more sources to get where we want to go than it used to. And there is no reason not to leverage that for our computing procurements. So that means when you want to get together all of your collaborators and put out a proposal, and for the vendors to be able to get together and cooperate on a response. It's really a win for everybody. And we just think that heterogeneous computing, right, accelerator-based computing, it's a viable path to Exascale, and it's the one that we have embarked upon at Lawrence Livermore. It may not be the only viable path, but it's one that we're going to do. Now, I have a short video. It's 2 minutes long. It doesn't have any sound. But it kind of trivializes probably the busiest time of my life over the last several months into 2 minutes of people running really fast. So this is our machine room floor. You can see I'm putting in the water cooling. That's the blue pipe. You can see electrical going in. We're working in parallel, so they're putting the infrastructure part of the computer together in that center part while we're still building the electrical and the water and everything underneath. They work really fast. That's good.
Is this the same room as the Blue Gene?
It's a mirror image room. So the wall to the left of most of this screen, on the other side of that wall is where Sequoia still is. So we have to be able to run both of these computers at the same time because we don't want to tell the scientists to take a year off while we build a new computer. They might like that, but the taxpayers would not like that. So you can see we've got the ISO base down. That's our earthquake protection because we are trying to have computers here in California. All these racks are empty at this point. And then the compute nodes will start to fill in later. This video only goes through about the end of December. But that got us to 25% of the computers installed. Now we're over 50%. So you'll see there's the first compute nodes are starting to power on. Those are actually the back sides of those nodes. Those are the lights on the power supplies that we're seeing. When you're giving tours of a computer center, people always want to see the blinking lights. And those of us in the industry know that blinking lights are becoming few and far between, right? So now we're putting more nodes in the rows behind that. You know, this is a very preliminary time-lapse video. We have more angles, and we're still taking footage, but I just wanted to show you guys what goes into this thing. So now we're bringing in the file system and building up the infrastructure in the middle part. And you'll see it start to fill in from kind of top left to bottom right. And that's the whole file system. So we've already got the whole file system in place, over 50% of the compute nodes.
You don't use hot aisle, cold aisle?
We do have hot aisle, cold aisle. So if you look in the foreground there, that's the front of that rack, but it doesn't have any computes in it yet. And then the back of the adjacent rack. So you've got a cold aisle in front, and you can see the vented tiles there for the cold air. And if you look just behind it here, you'll see this is a hot aisle. So it doesn't have vented tiles here. And then there will be vented tiles in the ceiling above it for that hot air to exhaust. Our computer floor is on the second floor, so we have positively pressurized cold air underneath. It comes up through the computer, up into the ceiling, and then it actually recycles back down through the walls. That's how we get that huge wide open space with no air handlers and no electrical equipment to be able to site a computer like this without having to kind of work around stuff. So that's what I have. we're running about the same amount behind as when I started, so I haven't messed us up too bad. But I do think there might be a little bit of time for some questions if anybody has any. Yeah?
Looks like you're getting about 10 gigaflops per watt. What's the target over the next 2 years? Do you have a feel for that?
So the short answer is no, we don't have an exact gigaflops per watt target. But the longer answer, slightly more nuanced, is that when you change onto a new technology curve, right? When you make a disruptive change onto a curve, you see amazing increase in flops per watt. So when we went from the ASCII purple system that was, IBM Power 5, fat nodes, right, to BlueGene-L, which was basically embedded processors with lots and lots of processors, we were able to, make a big quantum change with no slope in flops per watt. By going to GPUs, we did the same thing, right? We were able to make this quantum change. We don't see another quantum change before Exascale. So the next generation of systems we think will look a lot like this in terms of flops per watt. So what we've done is we've got an Exascale computing facilities modernization project going on where we have to go to Congress and say, we need a bunch of money, and the reason we need it is to modernize this facility for Exascale computing. We need 80 megawatts in the building. So not all of those will be for that computer, but clearly that says that we need, we might get some improvement in flops per watt, but we're not going to be able to get it all from flops per watt. We're going to need more watts. Yeah?
So Adam, I'm assuming most of your applications are homegrown or community shared applications, and you're continuously enhancing the physics, the complexity of models and solvers. So how do you ensure performance portability? Because some of the code optimizations and performance enhancements that you've done for the previous edition that you get undone.
So one of the things that we do as we're porting an application is we also continue to baseline the new code against the old platform, right? That's why Sequoia is still there. And our CTS systems are sitting right next to these. In fact, in the back corner of this, that's Zin and Jade, which are our two big CTS classified platforms. So you do that, but you also try to abstract, right? So that's what Raja is about, is making an abstraction layer that allows you to describe where the parallel portions in your code are, right? Where is the parallelism, and what are your data requirements? I didn't talk about Chai, but Chai is another open Livermore project that does what Raja does, but for data. And so you basically tell the abstraction layer where the parallelism is, and then you have to trust the abstraction to make any necessary transformations and optimizations to actually unlock that parallelism on the architecture. This is new stuff, right? It's not guaranteed to work perfectly for every architecture, for every code. But this is where we think we can go, and so far the results are really encouraging. So I think we have last question, and then we're going to go on.
So Coral is doing research in nuclear weapons. Could you consider, or is anyone considering using nuclear fission to power you?
So in California, we have a distinct advantage that we have a lot of renewable energy sources already, right? So our power comes both from PG&E, which is the local power grid, and WAPA, which is the Western Area Power Authority, which is hydropower, right? That's managed by the federal government. So that's how we're currently getting our power. There are a lot of pluses and minuses to nuclear fission power. And I think it's more a political issue than a scientific issue, right? And I'm mostly here to talk about science. I'd like to thank everybody again, and I'll be around, so come up, say hello, we can talk about computers.